Hi everyone, it's Mrs. Tucker. I was going to put this at the end, but it probably makes more sense to put it at the beginning. I created this form called It's Radical, and it reviews everything that we've done in this unit, with the exception of Pythagorean theorems, so make sure you study that. It's just a real skills and drills practice. So in case you don't have this form, I'm just going to show you a video of each of the pieces of the form, and you stop the video. The video works with you, tutors you on all of the odd problems, okay? You work the even problems. Really, ultimately, what I'd like you to do is work everything on your own and then check your answers with the answer banks. But I know some people need a little more extra guidance with all of this radical stuff. That's why I'm going to work the even problems with you. Okay, so what I'm going to do is I'm just going to pop up each one of these sections. You can pause the video. If you don't have this form, pause the video and just write the problems down and start working them. Okay, so pause the video. Let me pop up the next section. All right, here's the next section. Pause the video and write those down. Work those problems. Let me make this bigger so you can see it. Okay, this is page 2. Pause the video. There's the rest of that page. Pause the video. Here's page 3. I guess there is some Pythagorean theorem in there. I just don't work one with you. Okay, so pause the video. There's the rest of that page. Pause the video and write down these problems. Work them. And here's the last page. Okay. This is all about complex numbers, so pause the video and write those down. Okay, and I'm guessing you got H and I. I have to scroll just a little bit more, and that gives you the last 3 problems and the answer bank. And the answer bank's all in order. All right? Challenge yourself and see if you can work all the problems. Some of these my group is going to work in class. My group, I'm going to have them work the even problems in class. As a backup, they've got this video for the odd problems. Okay? Hi everyone, it's Mrs. Tucker. I'm going to help you guys get ready for this test by going through this little worksheet that I created based on some tutoring sessions I've done in the past. I pulled all the little scratch pieces of paper together, the problems that we worked in tutoring sessions, and put them all on this one big sheet. Okay, so I think what I'm going to do is I'm going to go through and do the odd problems, because when we're in class together, I'm going to have you in your groups work the evens. All right? So you'll have a helper or a table of help with the evens, and I'm going to help you with the odds. How does that sound? And if you'll notice, at the end of this sheet, there's an answer bank. And so I'll definitely make sure that I put that up there. If anybody that's not on my roster wants a copy of this sheet, let me know and I'll email it to you or I'll text it to you. And you can either print it off at home or print it in the math lab. How's that sound? Okay, so we are going to work today together. We're going to do all the odds. All right, so let's start with the first section. This comes from 10.3. It says simplify each expression completely. And I have told all the people in my group that you can't take that chart perfect squares, perfect cubes. You can't take that chart in the test with you, but you certainly can create your own. So I think I would take maybe, a few minutes at the beginning of the test and create a perfect squares and a perfect cubes chart, because I think that might help. Yeah, it's always nice to have a little reference point. It doesn't take too long to put this together. Okay, so number 1 says, simplify each expression completely. Right here, when we have the square root of 72, I want to find the largest perfect square factor of 72 if it exists. And I'm guessing it probably does. And sometimes looking at the chart definitely will help you, because I see that 9, I know that 9 is a factor of 72, okay? There might be a larger number that's a factor of 72. So if you don't know, what we can always do is take 72 and bust it down into prime factorization and see if we can't find a larger perfect square factor that way. Or sometimes if you can break it up into just 2 pieces, each piece has its own perfect square factor. All right, so I'll show you. I know 72 is divisible by 9. 8 times 9 is 72. 9 is 3 times 3. 8 is 2 times 4. And 4 is 2 times 2. Okay, so I have 2 times 2 times 2 times 3 times 3. When you get it down to its prime factorization, since our index here on our square root is a 2, well, that's not a very good looking 2. Let me try again. Our index is 2. We're grouping up identical pairs of numbers. There's an identical pair. We're just grouping up in 2s. So 2 times 2 is 4. That's a perfect square. 3 times 3 is 9. That's a perfect square. I have 4 times 2 times 9. If you take 2 perfect squares and multiply them together, the 4 times the 9, that gives you 36 times 2. And if you look at your chart, 36 is a perfect square. Okay, so I know it's 36 times 2. So we're going to call this the square root of 36 times 2. Using our multiplication property of radicals, I know that's the square root of 36 multiplied by the square root of 2. The square root of 36 is 6. The square root of 2. That's our answer. 6 the square root of 2. All right? Let's take a look at number 3. Number 3 is the square root of x to the 15th. All right, well, we don't have a number now. We have to deal with variables. So if I have x, you know what, I don't even need that crossbar. Let me just do away with that. Let me just do this. If I have x and I square it, come on, square it, I get x squared. If I take x squared squared, looks like this. Or you could say, well, that's x squared times x squared. If the bases are the same, you add your exponents. Power to a power, multiply your powers. You get x to the 4th. Next, we're going to take x third. So that's x to the 1, x to the 2, x to the 3. X to the 3 squared means x to the 3rd times x to the 3rd, which gives you x to the 6th. We're not there yet. X to the 4th squared, x to the 4th raised to the 2nd power. Power to a power, multiply your powers. Do you guys see the pattern here? Squares, our perfect squares are x squared, x to the 4th, x to the 6th, x to the 8th. What comes next? Yeah, they're all even powers of the variable. Here's x to the 5th. We're not there yet. Then comes x to the 12th, x to the 14th, and then x to the 16th. X to the 16th goes over because we only have x to the 15th. So here we've got x to the 7 and x to the 6th. The largest perfect square factor in x to the 15th is x to the 14th. So we can say that square root of x to the 15th is x to the 14th multiplied by another x, or x to the 1st. Because x to the 14th times x to the 1, bases are the same, you add your exponents, you get x to the 15th. So we can say that is the square root of x to the 14th times, let me try that again. There we go. Times just the square root of x. And what's the square root of x to the 14th? Yeah, x to the 7th times the square root of x. So that's our answer over here. X to the 7th, the square root of x. That's our final answer. Okay, and there is kind of a neat little trick right here. What's our index on a square root? Yeah, that's 2. I've just shown you that all of these even exponents are perfect squares. What's the relationship between the square and the square root? If you take 2 and divide by 2, you get 1. If you take 4 and divide by 2, you get 2. 6 divided by 2 is 3. 8 divided by 2 is 4. 14 divided by 2 is 7. Okay, just a little shortcut there that you can use. All right? Let me just go back and I'll just erase all of this because I want to keep my chart. All right, we've done 3, 5, 1, 3. Let's do number 5. Number 5 says, the square root of 50, x to the 7th, y to the 8th. I need to find my largest perfect square factor of each one of these factors. Okay? Take a look at your chart. Do you see a large perfect square factor of 50? Because I do. I know that 25 times 2 is 50. So I can say, well, that's the square root of 25 times 2. What's the largest perfect square factor of x to the 7th? Yep, let's take that down. Let's take x to the 7th down to x to the 6th. X to the 6th is a perfect square factor because it's divisible by 2. So x to the 7th, we're going to rename that x to the 6th times x. And then y to the 8th, since that's even, it is a perfect square factor. Now let me put that little index of 2 in here because that's going to help us with the variables. All right, what's the square root of 25? The square root of 25 is 5. We're going to have to leave the square root of 2 as it is because there's nothing you can do with it. What is the square root of x to the 6th? Well, I just showed you a little trick. Take that even number of 6 and divide by your index of 2 and you get what? X to the 3rd. Because x to the 3rd times x to the 3rd gives you x to the 6th. We have to leave the x under here. And then y to the, what happened to my 8? Y to the 8th, we're taking the square root. Y to the 8th is a perfect square. What is the square root of y to the 8th? Take that 8, since it's even, divide by 2, and you get 4. And there is your answer. Okay? All righty. I could say that a different way. If you need me to, just let me know. Text me and tell me I did number 5 and I still don't get it. And then I'll do it a different way for you. I always try to pick the easiest way, but easiest in my mind isn't always easiest in your mind. All right, so let's erase this and we'll do number 7. All right, number 7, we are adding. If you're adding radicals, basically you're combining like terms. You have to have like radicals in order to combine these. Here I have 7 square roots of 5 and I'm adding 3 square roots of 5. So if I take 7 of them and add 3 to them, I get 10 square roots of 5. All right. A hint on number 8, square root of 6 is simplified, and the square root of 6 is simplified, and these two are like radicals. 72 is not simplified. You've got to find the largest perfect square factor there and take the square root of it and get it out. You might be left with the square root of 6 here also. I don't really know, but that's just a hint. Okay? All right, in the next section, this all came out of 10.4. We're going to add, subtract, and or multiply each radical expression, simplify the answer. All right, on number 9, I have 20, the square root of 20x to the third, and I'm subtracting x times the square root of 80x. So the first thing you want to do in each one of these square roots is see if you don't have the largest perfect square factor in each one of those expressions, okay? So 20, let's see, does 20 have a perfect square root on our square root chart? Right there, it's 4 times 5. So I know this simplifies, well, an intermediate step is 4 times 5 times, what's the largest perfect square factor of x to the third? Yeah, that's an odd exponent. Let's take it down 1 and call it x squared. X squared is a perfect square times x. X squared times x gives us x to the third. All right, let's pull out, let's take our square roots of our perfect squares. What's the square root of 4? That's 2. So we took care of that. Here's our other perfect square. What's the square root of x squared? That's just x. And we have to leave inside the radical 5x. All right, so we've dealt with this first term here. Let's deal with the second one. All right, here we're going to be subtracting. Well, I know there's an x on the outside. We have to deal with the square root of 80 times x. X is not a perfect square. I know it's going to stay under the radical sign. Now with 80, I need to find the largest perfect square factor of 80. And looking at this chart, do you see it? It could be 4. Is there anything larger? If you don't know, go ahead and use your factor tree. I know that 4 is a factor. 4 divides into 80 20 times. And 20 is 4 times 5, and 5 is prime. Okay, I grouped these two 4s together. 4 times 4 is 16. 16 is your largest perfect square factor of 80. So that's going to be 16 times 5 times x. All right. What's the square root of 16? Yeah, that's 4. So I'm going to park that out front of the x. When I pull it out, you know, the square root of 16 is 4. There's nothing we can do here. So the square root of 5x stays inside the radical. And look at what we have here. We have like radicals. The square root of 5x and the square root of 5x creates like radicals. So I have 2x, the square root of 5x, subtract 4x, the square root of 5x. We are just going to deal with this part right here. And this part is a like radical with that part. 2 subtract 4 equals what? Let me erase all of this over here. Did you get negative 2x, the square root of 5x? That should be our answer. Okay? Okay, on the paper copy at the very end, I do have an answer bank for you, and it's all in order. And so you can see on number 9, we got the right answer. All right. Okay, so let's go back to where we were. I think we were that's not where we were. Here's where we were. Okay, we did number 9. Let's take a look at 11. All right, 11 says we've got the square root of 3 being multiplied by the quantity, the square root of 12, minus 6, the square root of 3. What are you going to do first? You are so right. We are going to use distributive property. You know what, let me see if I can blow this up real quick. Sometimes it's nice just to get them by themselves without all the other distractions. There we go. You can just focus on number 11. So I'm going to use distributive property, and I'm going to take the square root of 3 and multiply by the square root of 12. And then I've got square root of 3 multiplied by this negative. Positive times negative is negative. Watch your signs. So I'm going to take this and multiply by that. So I have 6, the square root of 3 being multiplied by the square root of 3. All right? So let's see what we've got here. I can say this is, I can combine this all together and say this is 3 times. Well, I know that 12, isn't 12 3 times 4? Or you could just say 3 times 12 is the square root of 36, because 3 times 12 is 36, and the square root of 36 is 6. All right, let's go look at the next part. We're subtracting. What happens when you take the square root of 3 and multiply by another square root of 3? You've got the square root of 3 being squared, and that undoes one another. Or you could say you've got the square root of 9. It's the same as the square root of 9, which is 3. So I've got 6 times 3. And 6 times 3 is 18. What is 6? Subtract 18. Negative 12. Yep, we got the right answer. All right, moving on. Let's see, we did 11. Let's look at 13. Okay, on 13, they're asking us to take the quantity of the square root of 13 plus x and multiply it by the quantity of the square root of 13 minus x. So how are you going to do that? I have a binomial times a binomial. That's right, we're going to use FOIL. We're going to FOIL this thing out. Okay, so let's take the square root of 13 times the square root of 13. That's my front two terms. I have the square root of 13 times the square root of 13, or the square root of 13 squared. I always have troubles getting that little tiny 2 in there with my pen. All right, let's do our outside terms. I have a positive times a negative, which is negative. And I have x times the square root of 13. X times the square root of 13. Let's do our inside two terms. Positive times positive is positive. X times the square root of 13. X to the square root of 13. Then our last two terms, I have a positive times a negative. So that's negative, and I have x times x. That's x squared. Okay? Let's go through and simplify everything. If you're taking the square root of 13 and then turning it around and squaring it, these are inverse operations. We're left with 13. Here I have negative x, the square root of 13, plus x, the square root of 13. That creates a 0 pair. It drops out. And I'm left with 13 minus x squared. There's nothing you can do. That's the answer. So 13 is 13 minus x squared. 13 minus x squared. I thought I copied the answer bank in here. There we go. 13 minus x squared. We're good. Let's take a look at 15. All right, where is 15? Must be on the next page. There we go. Let me blow it up a little bit if I can. Okay. My computer's being a little ornery. Oh, there we go. Let's find 15. And I'm going to copy it onto its own page. There we go. Okay, this is an addition and subtraction problem. When you're adding and subtracting, oh, what is this section called? I guess we're still adding, subtracting, and multiplying. When you're adding and subtracting, you're combining like radicals. All right, so we're going to have to pull out our largest perfect squares out of any numbers under the radical sign and out of our variables. So let's just take this a step at a time. Let's deal with this one first. What's the square root of 4? Yep, that's 2. And x to the 7th is not a perfect square because that exponent's not even. So I'm going to call that x to the 6th times x, or x to the 1. X to the 6th times x to the 1 is x to the 7th. What are we going to do with the y? Yeah, that's not an even exponent, so we're going to drop it down one, call it x to the 4th, y to the 4th times y to the 1st. That gives us y to the 5th. Now that we've done that, here's our largest perfect square factor in x to the 7th. Here's our largest perfect square factor in y to the 5th. And they come out of the radical sign. What number or what variable times itself? X to the what power times x to the what power gives you x to the 6th. Yeah, and the little trick was if our index here is 2, remember, take the 6 and divide by 2. We get 2 x to the 3rd, because x to the 3rd times x to the 3rd gives us x to the 6th. Let's look at y to the 4th. What y exponent times itself gives you y to the 4th? Yeah, that's y squared. Take the 4 and divide by 2. You can double check. Y squared times y squared is y to the 4th. So we've dealt with that, and what's left under the radical sign is x, y. Okay? Let's do this part here next. Plus, we've got 9x squared on the outside. Y to the 3rd, what's our largest perfect square factor of y to the 3rd? Yeah, just drop down your exponent 1. That's, did I say y? I meant x. X to the 3rd. Your largest perfect square factor is x squared times x. And with your y, once again, just like right here, you've got y to the 4th times the y. Y to the 4th times y. That's a perfect square, and that's a perfect square. So let's pull those out from under the radical sign. So I've got 9 times x squared times, okay, take your 2 and divide by your index of 2. It's parked right there, and you get x. Y to the 4th comes out as what? Y squared. Y to the 4th, take that 4, divide by your index of 2, and you get y squared. What's left under your radical sign? Yep, just an x, y. And this will simplify even farther because 9, take this x squared times an x, and you get what? 9x to the 3rd, y squared, and the square root of xy. All right, let's deal with the last one here. We are subtracting 5x, y. X to the 5th is not a perfect square. What's the largest perfect square factor of x to the 5th? Yeah, that's x to the 4th times x, or x to the 1st power. Y to the 3rd is not a perfect square. What's the largest perfect square factor of y to the 3rd? That's y squared times y. This is a perfect square, and this is a perfect square. So let's take those out of the radical sign. So we're subtracting 5 times x times y. Our index here is 2. Man, with my little pad here, it's really hard to draw that in real small. X to the fourth squared gives you what? Or square root of x to the fourth gives you, we're going to multiply. When I take the square root of x to the fourth, I get x to the what? Yep, squared. So we took that out. Y squared, taking the square root gives you what? The 2 divided by 2 is 1, so it comes out as y. We've dealt with that. What stays under the radical sign? Yeah, your x times y. Let's simplify this. This x times an x squared gives you what? And we've got 5 x to the, I've got x to the 1 times x to the 2 gives me x to the 3. Y times y is y squared. The square root of xy. I'm going to go ahead and bring this down. 2x to the third y squared, the square root of xy. Okay, do you see what I see? Are you seeing what I'm seeing? This right here is the same as this right here, which is the same as this right here, and we have like terms here. When everything else except for the coefficients the same, you have like terms. So I'm going to take 2 plus 9, which is 11, and 11 subtract 5 gives you 6. X to the third, y squared, the square root of xy. Woo! Yeah! Yeah! What did you think about that one? I know. So 15. Yep, it matches. And we are good. All right, number 17. Here we're dealing with cube roots. So we've got to go in and see if we don't have a perfect cube factor of 108 and of 32. So I've got my little handmade chart here. When you look at this, I think 32 is probably easy to find the perfect cube root, because when I'm looking at this, I know that 8 times 4 gives me 32. So here, let's deal with that part first. I can say cube root of, another name for 32 is 8 times 4, and 8's a perfect cube, because 2 times 2 times 2 gives me the 8. So the cube root of 8 is what? Whoops, we're subtracting here. Cube root of 8 is 2. So I'm going to say this is 2, the cube root of 4. There's no number times itself that gives you 4. I don't see it on my cube root chart. So I've simplified that term. Let's go and simplify the other term. And 108, I don't know, I look at this cube root chart and nothing really pops out at me. So in that case, I'm going to use my factor tree. And 1 plus 0 plus 8 gives me 9. If the digits add up to something that's divisible by 3, the number is divisible by 3. So take 108 and divide by 3, and you get what? Yeah, I get 36. Well, that's a perfect square, but we're looking for perfect cubes, so don't stop there. I know that 36 is divisible by 3. 3 goes into 3 once, 3 goes into 6 twice. That's 12. 3 times 12 is 36. Keep going. 12 is divisible by 3, and that gives you 4. And we can stop right there because I see a perfect cube right here. What's 3 times 3 times 3? Yep, that's 27. So I'm going to say this is -2, the cube root of 27 times what? Times 4. And the cube root of 27 is what? Yep, 3. So I've got -2 I take that cube root of 27, get 3, so it's times 3, the cube root of 4. So negative 2 times 3 is negative 6. The cube root of 4 minus 2, the cube root of 4. And looky there, we have like radicals. Cube root of 4, cube root of 4. So what's negative 6? Subtract 2. Negative, what'd you get? It's negative 8, the cube root of 4. There's our answer to 17. Negative 8, the cube root of 4. And somewhere in here I've got my answer bank, 17. There we go, we're good. All right, let's go find 19. There's 19. Rationalize the denominator and simplify. Okay, we don't like this radical down in the denominator. I want to get rid of it. I'm going to multiply by a form of 1. So you take that radical and you say, well, let's multiply by the square root of 4 over the square root of 4. Square root of 4 divided by square root of 4 is 1. This will get rid of the radical in the denominator. Because when I take the square root of 4 times the square root of 4, I get the square root of 16, and the square root of 16 is 4. Yeah. Okay, up here, 25 is a perfect square, and 4 is a perfect square, and I'm multiplying these together. What about x to the third? Okay, I've got the square root of 25 times the square root of x to the third times the square root of 4 in the numerator. 25 is a perfect square. Square root of 25 is 5. The square root of 4 is 2. And what's the largest perfect square factor of x to the third? Now drop that exponent down 1. X squared times x. What's the square root of x squared? Yeah, that's just x. So 2 times 5 is 10. The square root of x squared is x. And we have a square root of x left in here. So our numerator simplifies to 10x, the square root of x. Are we done? No, because 10 and 4 are both divisible by 2. 4 divided by 2 is 2. 10 divided by 2 is 5. Our final answer is 5x, the square root of x, over 2. Okay? Number 19. There you go. 2. All right. What was that? Number 19. 5x, the square root of x over 2. Okay, good. Let's take a look at 21. All right. You know, there's always a couple of different ways to approach every problem. So the way I'm working it out might be a little different than the way you work it out. And that's okay as long as you're following all the steps and all the rules. And, you know, let's take 21 and I'll show you 2 different ways to work this that gets us the correct answer. Okay? I've got the square root of 24, x to the 5th over the square root of 3. And we are rationalizing the denominator. All right, so one way to work this is to do this. I'm going to multiply top and bottom by the square root of 3. Square root of 3 over square root of 3. Right here, the square root of 3 times the square root of 3 is the square root of 9. And the square root of 9 is 3. All right, so I can multiply these 2 radicals together. And I can say, well, that is 24 multiplied by that 3 multiplied by x to the 5th. And 24 times 3 is 72. So we can say, all right, well, that is the square root of 72 x to the 5th. Okay, and do you remember what the largest perfect square factor of 72 is? Seems like we've been working it over and over and over again, doesn't it? If you can't remember, here we go. That's 8 times 9. 9's a perfect square. 8 is 2 times 4, and 4 is a perfect square. 9 times 4 is 36. So 72 turns out to be the square root of 36 times 2. That's those two numbers multiplied together. What's the largest perfect square factor of x to the 5th? That 5's not even, so drop it down 1 and make it x to the 4th. That's even. Times x, and that's all over 3. Okay, let's pull out our perfect squares. The square root of 36 is 6. The square root of x to the 4th is what? Take the 4, divide by your index. Yep, x squared. And what's left in your radical sign is, we dealt with that, and we did that. So 2x. And look, 6 is divisible by 3. If you divide 6 by 3, your denominator goes away, you just have 1. And 6 divided by 3 is 2. So there's our answer. Let me show you another approach you could have done. You could have looked to see if you wound up with something in the numerator that canceled out with what's in the denominator. So we could have done this. And I don't know, I was just playing around with this when I came across it. 24 is, let's see, 24 is 4 times 6, and 6 is 2 times 3. And let me write it that way, because this was kind of interesting. 4 times 2 times 3 times, okay, our largest perfect square factor of x to the 5th is x to the 4th times x. Okay? Let's do this. I'm going to say the square root of 4 times the square root of 2 times the square root of 3, using our multiplication property, times the square root of x squared times the square root of x all over the square root of 3. And do you see what I see? This doesn't always happen, but occasionally it does. Those cancel each other out. So now we've rationalized our denominator. The only thing in the denominator is 1. So we don't even have to write a fraction anymore. Square root of 4 is 2. So we've dealt with that. The square root of x squared is x. And we're left with the square root of 2 times the square root of x, which is 2, the square root of 2x. And let's see. Oh, you know what? Whoops. Actually, why didn't y'all stop me? I wrote down the wrong number here, didn't I? And you probably caught it when I did it. This is an x squared. It was x to the 4th. That is x to the 4th. Why didn't y'all stop me? Okay, so now let's do this. Square root of 4 is 2. The square root of x to the 4th is x squared. And we're left with the square root of 2x. All right, now my answers match. I wouldn't have really thought to have started this way. My approach still would have been to do that. But, you know, it just happened to work out. So 2x squared, the square root of 2x, and check, we've got our answer there. All right, let's do 23. We're going to rationalize our denominator, and I have a binomial in the denominator. How are we going to get rid of a binomial in the denominator? Yeah, we're going to multiply top and bottom, numerator and denominator, by the conjugate of the denominator. What is the conjugate of the square root of 2 plus 1? Yeah, that's the square root of 2 minus 1. And you got to do it on the top. So we're taking that fraction and multiplying by 1, so you're not changing the value of the fraction. Okay, so we get 3 times the quantity, the square root of 2 minus 1, and in the denominator, the square root of 2 plus 1 times the quantity, the square root of 2 minus 1. Whew, what are we going to do in the numerator? Yeah, we're going to use distributive property. So 3 times the square root of 2 is 3 times the square root of 2. And 3 times negative 1 is negative 3. How do we multiply the two binomials together in the denominator? Yeah, we are going to use FOIL. Front two terms multiplied together. If I take the square root of 2 times the square root of 2, I get the square root of 4. And the square root of 4 is 2. You know, you don't have to do that many steps at one time. You can just say that's the square root of 4. It probably isn't wise to combine a whole lot of steps together. Okay, let's multiply our outside two terms. I have a positive times a negative. That's negative. And 1 times the square root of 2, square root of 2. Multiply our inside two terms. I have a positive times a positive. 1 times the square root of 2 is the square root of 2. Let's multiply our outside two terms, our last two terms. I have a positive 1 multiplied by a negative 1. That is negative 1. Okay? Yeah, don't combine too many steps. It gets real confusing. Okay, in the numerator, we still have 3. The square root of 2, subtract 3. In the denominator, the square root of 4 is 2. Here I have a minus the square root of 2 plus the square root of 2. That's a zero pair. They cancel each other out. And we have that minus 1. 2 minus 1 is 1. Our denominator becomes 1. And it disappears. So we're left with 3, the square root of 2 minus 3. 3, the square root of 2 minus 3. Right there. Okay? All right. Let's take a look at 25. Okay, this is from 10.2, and it says simplify. Write the answers with positive exponents. They don't want the answers in radical form, they want it in exponent form. All right, here in the numerator, I've got a power raised to a power. If you've got a power raised to a power, how do you simplify that? Power to a power, multiply your powers. How do you take 2 and multiply by 1/3? I hope by now you guys have noticed when you take a whole number and multiply by a fraction, that whole number gets multiplied by your numerator. If I do this, can you see that? Yeah, so this is going to become a to the what power? 2/3 over a to the 5/3. Here our bases are the same when we're dividing. Do you remember that rule? If bases are the same and you're dividing, then you take the base and you take your top exponent and subtract your bottom exponent. All right? So that gives us a to the, what's 2/3? Subtract 5/3. 2/3, take away 5/3, is negative what? 3/3. And another name for negative 3/3 is what? A to the negative 1. This says write it with positive exponents. Do you guys remember the definition of a negative exponent? X to the negative n power is the same as 1 over x to the positive n power. So we're not done yet. The final answer is what? 1 over a to the positive 1 power. If we don't have to write the positive 1 power, we're done. There's 25. 1 over a. (25) 1 over a. We are good. Oops. Let's do 27. Solve each radical equation. Okay. When you are solving radical equations, it is possible to introduce an extraneous solution. That's a solution that does not satisfy the original radical equation. You must check all your answers. Okay, 27. I have the square root of 2x equals 5. I can undo the squaring of the number by squaring it, right? That leaves me with 2x on this side, but what you do to one side, you must do to the other. So 5 squared is 25. I want to get x by itself. I have to get rid of multiplication by 2. So I'm going to divide by 2. And I get x equals, I'm going to leave it as 25 halves. Because I need to take that answer and plug it back into the original. So I'm going to take 2 times 25 halves. Now, if you do this and you multiply, you get 50 over 2, which simplifies to 25. 50 divided by 2 is 25, or you can just do this. Those will cancel each other out. So I have the square root of 25. Does that equal 5? Well, the square root of 25 is 5, and 5 equals 5. So we've done our check. That's our answer. And it's okay to leave it in improper form. You know, if you want to change it to a decimal, that's fine, but it's okay to leave it improper. And there you go, 25 halves. Let's go take a look at 29. Okay, with this radical equation, I just have a square root on the left-hand side. So to get rid of the square root, we'll square that whole side. And because I squared this whole side, you know, what you do to one side, you have to do the other. We have to square this entire side. All right? So on the left-hand side, we just have 4 minus x, because taking a square root and then squaring it, those are inverse operations and they undo one another. Over here, what I've got is x minus 2 being multiplied by itself. So we're going to use what to multiply these two binomials together? Yes, we're going to use FOIL. Here we go. X times x, x squared. When I multiply my outsides together, I get negative 2x. When I multiply my insides together, I get negative 2x. Combine those together and you get what? Negative 4x. Multiply my last two terms together, negative 2 times negative 2, positive 4. Okay, we have a quadratic here. And up to this point, we've only taught one way to solve a quadratic for x. Do you remember what that is? Yeah, it's that F word. We are going to have to factor it. But in order to factor it, we've got to set the equation equal to 0. All right? So this side over here needs to be 0. We need to get rid of these guys. So that's a positive 4. We're going to subtract 4. And what you do to one side, you do to the other. We're going to subtract 4 here. And those two terms cancel each other out. So over here I'm left with negative x. How do you remove negative x from this side? we will add x. And what you do to one side of an equation, you must do to the other. So on the left-hand side, we're left with 0. Right-hand side is x squared. What's negative 4x plus an x? Yeah, negative 3x. And that's all we have. Okay? This one here is not a trinomial, so we can't factor, down into two binomials. The only way you can factor this binomial here, these two terms, is to pull out a GCF. What is your GCF? Yeah, what's common in both of these terms? An x. So we have x times what gives you x squared? Yep. X times what right here gives you negative 3x. Yeah, it has to be a negative 3. Now, do you remember our zero product property or zero factor theorem? It's got a couple different names. If you've got one number times another number, or a times b equals 0, if the product is 0, then either the first factor has to equal 0, or the second factor has to equal 0. So we set both of those factors equal to 0. Well, in this case, x equals 0, or here we'll add 3 to both sides. We get x equals 3. Before I go wrapping boxes around these, I have to double check in the original. It is an absolute must. You've got to go back to your original, plug those answers in, and make sure they work. Okay, let's take the x of 0 and plug it in. Let's put in a 0 here and a 0 here. So I'm left with 4 minus 0 is 4, and 0 minus 2 is negative 2. Is the square root of 4 equal to negative 2? Well, they're wanting the principal square root here, and the principal square root of 4 is 2, and 2 does not equal negative 2. So 0 is not a solution. Let's try the other solution. Let's put in x of 3. So we're going to have the square root of 4 minus 3. Does that equal 3 minus 2? Well, 4 minus 3 is 1. The square root of 1 is 1. And 3 minus 2 is 1, and it checks out. So our answer here is the square, x equals 3. It's the only solution that works. X equals 0 was that extraneous solution. It did not work. There we go. Let's go do 31. Okay, we have a radical equation here. And I think you guys know what to do by now to get rid of the radical. And it's a square root. We're going to square it. What you do to one side, you have to do to the other. X squared equals what over here? Yeah, just 6x minus 8. Because squaring a square root undoes one another. We have a quadratic. How do you solve a quadratic? We just talked about it. You have to use that F word. Now we're going to have to factor. But before we can factor, we have to put our quadratic in standard form. Ax squared plus bx plus c equals 0. So here I need to move this positive 6x to the other side. I need to subtract 6x here, which means I'm going to subtract 6x here. So I have x squared minus 6x equals minus 8, negative 8. I need to take that negative 8 and move it to the other side. To get rid of it over here, I have to add 8. So I'll add 8 over here. And negative 8 plus 8 is 0. So let's get rid of that. Now we have our quadratic in standard form, and it is a trinomial. It should factor into two binomials. And I know an x goes here and an x goes here. I need factors of 8 that add up to negative 6. I need factors of 8 that add up to negative 6? Well, if you take 1 times 8, that is 8, but when you add them together, you get positive 9. So you know you need 2 negative factors. Negative 1 times negative 8. Negative times negative is positive, so that gives you negative 8. You add those together, you get negative 9, but we're looking for negative 6. So let's try negative 2 times negative 4. Negative 2 times negative 4 is positive 8. Negative 2 plus negative 4 is negative 6. That's what we were looking for. Negative 2, negative 4. Before you go on, double check with FOIL. I do this all the time. And here we are in the middle of CPM4. Front 2 terms gives me x squared. Outside 2 terms gives me negative 4x. Inside 2 terms gives me negative 2x. Last 2 terms, negative 2 times negative 4 is positive 8. These two combine to form negative 6, and that gets me back to the original. Alrighty, so zero product property, or zero product theorem, or zero theorem, whatever they call it. If you've got A times B and the product is 0, then either that term has to be 0 or that term has to be 0. One of your factors has to be 0. Yeah, those aren't terms, those are factors. So that means that x minus 2 has to equal 0, or x minus 4 has to equal 0. Don't skip this step, because a lot of people that skip this step get this wrong, because they forget I have to add 2 here and add 2 here, so x equals 2. Here I have to add 4, and I have to add 4 here. X equals 4. I have 2 answers, but it was a radical equation. I could have an extraneous solution, and I've got to double check. So I have x equals the square root of 6 times my x minus 8. Let's drop in an x of 2. We'll put in a 2 here and a 2 here. I get 2 equals the square root. 6 times 2 is 12, and 12 minus 8 is 4. And the square root of 4 is 2. 2 equals 2. That one checks out. Okay, let's put in the 4. Let's put in a 4 right there and a 4 right there. So 4 and 4. 4 equals the square root. 6 times 4 is 24. 24 minus 8 is 16. And the square root of 16 is 4. And 4 equals 4. They both check out, and both are solutions. So 6 equals 2 or 4. All right? I really am just double checking my answer bank as I go along here. Just make sure I didn't make any mistakes in my answer bank. All right, so let's look at 33. Here we have the square root of 2x equals the square root of 1 minus 2x. Well, we've got radicals on both sides. That's okay. We know how to get rid of those radicals. I'm left with 2x equals 1 minus 2x. I've got x's on one side or the other. What do you want to do to get them on just one side? Yeah, I'm going to add 2x here and add 2x here. 4x equals 1. How do you get rid of division, multiplication by 4? Yeah, divide by 4. We get x equals 1/4. I just have one answer there. So let's go back and double check. We're going to pop it back in here. So I have the square root of 2 times 1/4. You know, I really just have to make sure that my radicands are the same. I don't have to go through the whole square root process if my radicands are the same. And over here I have 1 minus 2 times 1/4. So 2 times 1/4, 2 over 1 times 1 over 4. I hope you notice that your whole number gets multiplied by your numerator. So that's 2/4, which is the same as 1/2. Let's check this radicand over here. I have 1 minus 2 times 1/4. That's 1 minus 2 times 1/4 is what? Yeah, that's 2/4. That's the same as 1/2. So I have 1 minus 1/2. What happens when you take a whole and remove a half? Yeah, you're just left with 1/2. Our radicands are equal. We don't even have to take the square root because we're going to get the same answer. And I know my answer is x equals 1/4. X equals 1/4. Okay? Let's see. Looks like my numbering changes to letters. So we'll skip 34 and we'll go to A. Let's go see what A looks like. I don't even know that it's on this page. Yeah, I'm going to have to go to the next page. Okay, oh, this is complex numbers. All right, on the last page. Let me see if I can zoom in here. We're going to start off with A. And it says simplify. Write in terms of I. Simplify, write in terms of I. This was 10.7, complex numbers. All right. How do we define I? Yeah, it's the imaginary unit. We cannot take the square root of a negative number. So some smarty down the line decided, let's call the square root of -1 the imaginary unit I, and then we can work all these problems. So I can change the square root of -49, which you can't take the square root of a negative number and get a real number answer. I'm going to call this -1 times the square root of 49, which is the same as the square root of -1 times the square root of 49, which gives us, well, another name for the square root of -1 is I. I times the square root of 49 is 7. We're going to write that coefficient of 7 out front. This really isn't a variable, so I'm not certain I can call that a coefficient. I is not a variable. It's the square root of -1. Anyway, that is our answer. For A, our answer is 7i. Yes, 7i right there. Okay, let's go look at C. Okay, C, we've got negative the square root of 54. And the instructions on this said simplify, write in terms of I. Well, you know I is the square root of -1. There is no negative under this radical. Okay? So I'll show you how to deal with this in a minute. First, let's find our largest perfect square factor of 54. And we're looking for the negative square root, not the principal. So that's it's like taking -1 and multiplying by the square root of 54. And isn't 54 9 times 6? Yeah, that's 9 times 6. 9 is our largest perfect square factor of 54. So the square root of 9 is 3. So we have -3, the square root of 6. And there's nothing else you can do with that, but they want us to write the answer in terms of I. What they want is they want the answer in complex form. That A plus BI, where you have your real part and your imaginary part. Well, I can put an I over here, but B is going to have to be what? Yeah, we're going to have to make that 0. And then add that. And then we've got our complex number. All right? If we had just left it as -3 the square root of 6, we'd only just be including the real part. So you can turn any real number into a complex number by adding in a 0i. I mean, I don't know why you'd want to do that, but you can. Yeah, I know. You don't have to tell me. I already know. Let's see. Okay, so C is -3, the square root of 6 plus 0i. Let's go take a look at E. All right, here we are multiplying the square root of -5 times the square root of -10. And there was a question that came up that said, well, why can we not just use the multiplication property and say that's the square root of -5 times -10, which turns it into a positive? Why can we not do that? And I didn't have a real good answer in the lecture, so I did some digging. So here's one of the things I found, and it's the extended product rule, okay, to cover this situation, which has now been added to my PowerPoint. Okay, our multiplication property of radicals says if you have the square root of a times b, then that's the same as the square root of a times the square root of b. This is the part that we left out, where a is greater than or equal to 0, and b is greater than or equal to 0. They can be 0 or positive numbers. Or a or b can be negative. One can be positive, one can be negative, but a cannot be negative and b cannot be negative. Okay? Because the square root of, if you take the square root of a negative number, it can't be done. You get an imaginary number. Take a square root of a negative number, you get an imaginary number. Your answer should be imaginary, and here you've taken two imaginary numbers and turned it into a real number. And we can't do that. We cannot do that. And I found some more stuff. And then I found the square root of a is only defined for 0 or positive numbers. This is the reason. And if you work with complex numbers, well, then the property could be false. Yeah, you can't multiply the square root of a negative number times the square root of a negative number, which doesn't exist, and create a real number. So we just can't do that. So instead, what we're going to do, we'll work in the imaginary realm of complex numbers, and we're going to do this instead. Okay, multiplied by -1 times 10, which is the square root of -1 times the square root of 5 times the square root of -1 times the square root of 10. This is I. I is the square root of -1 times the square root of 5 times another I times the square root of 10. That gives me I times I. That's I squared times, now you can take the square root of 5 and multiply by the square root of 10 and get the square root of 50. You know 50 is 25 times 2. 25 is a perfect square, so that's 5 to the square root of 2. So I get I squared times 5, the square root of 2, and I squared, if you take I, which is the square root of -1, and square it, then I squared equals -1. So here we get -5, the square root of 2. There you go. Okay, on G we are dividing, and in the denominator we're trying to take the square root of a negative number, which can't be done in the realm of real numbers. So we are going to imaginary land. Okay, so let's introduce our imaginary unit. We just left real number land. Actually, let's not do that. The square root of 49 is what? Yeah, we'll just call that 7. This is going to be the square root of -1 times 10. which gives us the square root of -1 times the square root of 10. And the other name for the square root of -1 is what? Yeah, that's I times the square root of 10. Okay, so we have 7 divided by I, the square root of 10. And the more I get thinking about my approach, I really don't like my approach because I'm going to wind up with I in the denominator, and I don't know that that's allowed. I don't know if we like that or not. I personally would rather have my I in the numerator. So let me back up a few steps. Let me back up to right here. Yeah, let's just redo the whole thing. Let's rationalize the denominator. Let's do that. Let's take the square root of -10 over the square root of -10. Okay. Now be careful here. The square root of 49 is 7 times the square root of -10, which you can't do, so we're going to go into imaginary land. -1 times 10. And here I've got, we can't multiply those together and call it positive 100 because we're taking two imaginary numbers and creating a real result. So what if we do this? What if we call this -1 times positive 10, and this one right here, the same thing, -1 times positive 10. Well, the square root of -1 is I. So we're going to call this I times the square root of 10. And this right here is I times the square root of 10. And we're multiplying these two denominators together. So I'm taking I times I, which is I squared, and the square root of 10 times the square root of 10, which is the square root of 100. Now if I take I and square it, then I have to square this, and I squared is -1. You know, there is no number times itself that gives you a negative answer unless it's I, and you're playing in imaginary land. Yeah, so this I squared is -1, and the square root of 100 is 10. So in our denominator, we have -10. Let's see what we can do with the numerator. Let's call the square root of -1i. So I have 7i, the square root of 10 over -10. And you guys know the computer doesn't like a negative in the denominator. So you can put it in the numerator or park it out front. So it's -7i, the square root of 10 over 10. Okay? All righty. Let's look at the next one. That was G. I don't have the next one loaded up. Let's go get the next one. That was G. We're going to do I. If it says add or subtract, write the answer in the form of A plus BI. They want it as a complex number. So let's grab I, make it bigger so we can see it. We're taking one complex number and subtracting another complex number. Well, with this complex number, I've got 6 plus 5i, but here I'm going to distribute a negative. So that -1 times 8 is -8. Take that -1 times -i, and I'm adding I. Okay, we're going to take our real numbers and add those together. And we get 6 minus 8, which is -2. Now let's take these imaginary pieces, the plus 5i plus another I, and you get what? Plus 6i. There you go. It's a complex number. -2 is the real part, 6i is the imaginary part. Okay, here's the last one I'm going to do with you guys. I believe, yeah, it is. Let's look at the instructions first. It says multiply or divide, write the product in the form of a plus bi. So let's grab k and make it bigger so we can see it. Okay, I have a binomial times a binomial, and both binomials are complex numbers. So I'm going to use FOIL. Front two terms. I've got the square root of 3 times the square root of 3. I have the square root of 3 squared. Outside two terms gives me positive times negative is negative. 2i times the square root of 3. My inside two terms is positive times positive. 2i, the square root of 3. And my last two terms is 2i, well, it's a positive times a negative, which is negative. 2i times 2i, we'll just call it 2i squared for now. Okay? All right, let's simplify what we have. If you square the square root of 3, you get 3. Negative 2i, the square root of 3, plus 2i, the square root of 3 creates a zero pair. And then we're going to subtract, well, here you've got 2 times I times 2 times I, which is 2 times 2 times I, which gives you 4i squared. You guys remember what I squared equals? I squared is negative 1. So we have 3 minus 4 times negative 1. If you make that a negative 4 times a negative 1, negative 4 times negative 1 is positive 4. 3 plus 4 is 7. Okay, the answer is 7, but the instructions said to write it in the form of a plus bi. Our answer only has a real part, but we can create a complex number if you do what? Yeah, take 0 and multiply by I. Okay? So the last thing that I want to do here, I will put up the entire sheet so you can stop and look at all the even questions plus the answer bank. Hi everyone, it's Mrs. Tucker. I was going to put this at the end, but it probably makes more sense to put it at the beginning. I created this form called It's Radical, and it reviews everything that we've done in this unit, with the exception of Pythagorean theorems, so make sure you study that. It's just a real skills and drills practice. So in case you don't have this form, I'm just going to show you a video of each of the pieces of the form, and you stop the video. The video works with you, tutors you on all of the odd problems, okay? You work the even problems. Really, ultimately, what I'd like you to do is work everything on your own and then check your answers with the answer banks. But I know some people need a little more extra guidance with all of this radical stuff. That's why I'm going to work the even problems with you, okay? So what I'm going to do is I'm just going to pop up each one of these sections. You can pause the video. If you don't have this form, pause the video and just write the problems down and start working them, okay? So pause the video. Let me pop up the next section. All right, here's the next section. Pause the video and write those down. Work those problems. Let me make this bigger so you can see it. Okay. This is page 2. Pause the video. There's the rest of that page. Pause the video. Here's page 3. I guess there is some Pythagorean theorem in there. I just don't work one with you. Okay, so pause the video. There's the rest of that page. Pause the video and write down these problems. Work them. And here's the last page. Okay. This is all about complex numbers. So pause the video and write those down. Okay, and I'm guessing you got H and I. I have to scroll just a little bit more, and that gives you the last three problems and the answer bank. And the answer bank's all in order. All right? Challenge yourself and see if you can work all the problems. Some of these, my group is going to work in class. My group, I'm going to have them work the even problems in class. As a backup, they've got this video for the odd problems. Okay?